On to problem 13. Rank the following compounds by the number of gauche and diaxial interactions for the most stable conformation. For the most stable conformation means they want us to assume equatorial position when possible, because axial position is more unstable. Okay, so first we're going to name the 3 compounds we have given, and we want to look at basically their substitution, where those dimethyls ended up, since they're all cyclohexanes. So we have a 1,2 compound, a 1,3, and a 1,4. And since they're all wedges, we know that they're all cis compounds. So for these, we can again look at the table and know whether the branches are equatorial and axial, or we can do the odd-even method. Since this guy's odd and this is even and it's cis, odd-even means they're different. So one's axial, one's equatorial. 1, 3, they're both odd numbers. They're both going to be the same letter. And since we know that they want us to assume the most stable, we can assume both of these are equatorial position. Last for ring number 3, we have odd even again, so one of these is going to be axial and one is going to be equatorial. Okay, now we want to look at the interactions about these branches. So let's look at the gauche interactions for 1, 2, 1, 3, and 1, 4. Gauche interactions really will only happen with 1, 2. So we can look right away at 1, 3, and 1, 4 and say there's going to be no gauche interactions, or 0. That's because those don't focus on diaxial, which are reactions on top. If they're happening on the equatorial position or gauche interactions, one has to be in the equatorial or both, or one has to be in the equatorial and axial. So that'd be like 1, 2 here, and you could tell easily by the Newman projection that there's a 60-degree angle between those. Okay, so that for diaxial we have to assume is only going to take place in the 1, 2. But let's draw it out. We have one axial position and one equatorial methyl group. So looking at the Newman projection, we can see that one's going to be axial position on the 1 carbon, and this black line on this little crosshair is then 1 carbon, and then the one in the back is represented by that circle and is blue on that blue line. So we have that drawn out, and we can see 1 gauche interaction. The rest would just be hydrogens, so we're not even going to bother drawing those. Okay, back to these, we can say that there's 1 gauche interaction. Next, we'll look at diaxial interactions. For those, it'll only count if we have axial position carbons, obviously. And diaxial interactions are more, of course, if you have those axial position methyls colliding with other hydrogens. So a methyl group colliding on top on the 2 axial positions with the hydrogen and with the other hydrogen. So we can draw this out, and we'll draw out those interactions. We have those 2 hydrogens also in the axial position bumping into each other, and this one. So you can see those 1 and 2 interactions, and both of these diaxial interactions are between methyl groups and hydrogens. You can also have a diaxial interaction between 2 methyl groups, which is even more unstable or takes more energy to maintain. Okay, so we said we saw 2. Let's add that to our table. Okay, and for the next one we have 2 equatorial carbons, so we don't even have to worry. We should have 0. And our last one, we have another axial, which means we'll have again the same interaction. We'll have 2 because we only have 1 axial. There's no need to count. It's the same as before. Now we can add all those up, and see what our total number of interactions are. For compound 1, we have 3 interactions, 2 is 0, and 3 is 2. And they want most interactions first. Okay, so 3, 2, 1. 1 has the most interactions, then it's 3, so our answer is B. Okay, and now we shall move on to problem number 14. They want to know the highest energy conformation for trans 1,2 dimethyl cyclohexane and how many CH3 diaxial interactions there are. So again, we'll use our odd even or the table to figure out whether these are equatorial or axial position methyls. We have a 1,2 trans, so if it was cis, using my odd even, we have them being different, so axial equatorial. And if they were, since this one's trans, it's the opposite of that, so it's axial, axial, or equatorial, equatorial. And they want to know that in the highest energy conformation or more unstable. Axial, axial is way more unstable than equatorial, equatorial. Okay, so we can draw those out on these ring right here and count out to see whether or not there's a ton of diaxial interactions. 1, 2, so let's draw 1 here, assuming that's the first methyl, and then we'll assume this carbon over here is 2, and we'll draw it down here. If you know how to draw this chair pretty obviously, this will be easy for you. But let's draw the H's now, just to see where they're going to bounce into each other. Okay. Now let's draw those interactions. So we have one methyl group bouncing on top, another methyl group bouncing against the hydrogen up top, and then the ones on the bottom, the methyl group will bounce against these other hydrogens. So that makes for 1, 2, 3, and 4 interactions. This is easier to see on the ring now that we have it at 1, 3, 4. When you have them at 1 and 2 position, you're going to have one going upwards and one going downwards. That's where we get the odd even from, because the odd number chains, 1, 2, are all facing upwards. 1, 2, 3, and all the even numbers are facing downwards. So when you have an odd and an even number, one's facing axial, one's facing axial downward. Counting those interactions between the hydrogens, you can see that there's 4, just like what we drew out here.